For my presentation, I'll be talking about halogenation of drugs, more specifically pheneramin, which consists of a benzene ring and a substituent. So I'll be talking about the directing effects of substituents, electrophilic aromatic substitution, and yeah, the directing effects of substituents. I'll also be talking about how bromine and chlorine can make a pretty huge difference on pheneramin. So, yep. Last semester we learned the halogenation of alkenes. In this example, bromination. So we know that when we react Br2 with an alkene, the alkene acts as a nucleophile while Br2 acts as the electrophile. This is the case because the pi electron cloud from the alkene makes Br2 electrophilic when it approaches. So when the alkene attacks Br2, it forms this intermediate, which is positively charged. The negatively charged bromine, which was left over, then attacks the intermediate, giving us our product, which sadly cannot occur with a benzene ring as a nucleophile, mainly due to Br2 not being sufficiently electrophilic. So, okay. In order to make Br2 sufficiently electrophilic, we could add iron. In this case, if we were to add a chlorine atom to a benzene ring, we could use aluminum, but they both essentially do the same thing. In this case, if we want to add a bromine atom to the benzene ring, adding iron to the mix, iron and bromine would first react, forming iron tribromide, which actually works as a catalyst in the halogenation of benzene rings. We can see here that it is part of the final product when it is also part of our reactant. Or yes, so iron tribromide, keeps reacting with Br2, forming this complex, which is essentially our electrophile. More specifically, this positively charged Br2. That's our electrophile. So we know that the benzene ring is our nucleophile, so it attacks the positively charged bromine, forming this intermediate, the sigma complex, resonance stabilized. We can then see that the remaining iron tetrabromide deprotonates the sigma complex, restoring aromaticity and giving us our final product or products. So sometimes on the benzene ring there are substituents which actually direct where the bromine would appear on the benzene ring. For example, if we were to have, let's say, an electron donating group, it would not only direct the bromine, but it would actually make the reaction go a lot faster than if it were just to be a benzene ring alone. If it was a electron withdrawing group, it would do the opposite, and it would direct the bromine atom to a different position on the ring. For electron donating groups or activating groups, the bromine would be placed on the para position or the ortho position. It's usually placed on the para position due to sterics, making the final product more stable. Actually, this would be the uh, bigger product. And for electron withdrawing groups or deactivating groups, the the bromine would actually be placed in the meta position. In case for pheneramin, probably pronouncing that incorrectly, but pheneramin is an antihistamine which can be halogenated just like many other drugs. We halogenate drugs in order to produce new drugs or just enhance maybe the properties of the drugs we're working on. In the case for pheneramin, it is commonly used for allergies and even colds. So when it comes to pheneramin, if we were to halogenate it, or at least this benzene ring, it would occur on the para position, since this is an alkyl group, an activating group. I guess it can, the chlorine atom can show up in the ortho position, but due to sterics, it is not as stable as the para position. But when you add a chlorine atom to the para position for pheneramin, turning it into chlorpheneramin, it actually it makes it 10 times more potent than pheneramin, which is pretty insane and cool at the same time. You can also add a bromine atom, of course, turning pheneramin into bromopheneramin. The difference now is that it's just as potent as chlorpheneramin, but the difference is that the effects last twice as long, which is even more insane. Chlorpheneramin is more commonly known as chlortrimeton. I found out that it's discontinued, but I also found it on Amazon, so I'm not entirely sure what's going on with that. But yeah, these two new drugs, I guess, that were produced are pretty much better than this. They were just halogenated, and yeah, it's pretty crazy how much that affects the drugs. Obviously, it's not just with this drug. It could be done to a lot of other drugs, really changing its properties and well, making them better in this case, I would assume. So yeah, we can see how electrophilic aromatic substitution works in the pharmaceutical world. And yeah, that is all. That's my presentation.